controllable pixels generating light and color. The display must work in perfect harmony with the touch sensor. Any misalignment would make touches register incorrectly. Between these major components sit additional specialized layers, polarizer films controlling light passage, optical adhesives bonding layers together, and thin film transistors forming the electronic backbone controlling individual pixels. All these layers connect to a specialized controller chip, typically located at the edge of the screen. This touch controller is a purpose-built microprocessor dedicated to touch detection. It connects to the ITO grid through thin, flexible circuits and constantly measures the electrical properties at each intersection point. The controller samples the entire grid thousands of times per second, checking for capacitance changes, indicating finger touches. It can detect changes as small as a fraction of a picofarad while filtering out electrical noise from the phone's components, nearby electronics, power lines, and atmospheric electricity. Modern controllers can track 10 or more fingers simultaneously, measure pressure intensity, and even detect hovering fingers. Some recognize the unique electrical signature of water droplets and ignore them to prevent false inputs. Manufacturers add additional components for specific features. Fingerprint sensors under the display include specialized optical or ultrasonic sensors. Devices with stylus support contain extra sensing grids, and phones with variable refresh rates include additional control circuitry. All these components work together flawlessly while remaining completely invisible. When functioning properly, you never think about the complex technology sandwiched beneath your fingertips. You simply touch the screen and the phone responds, creating the illusion of direct manipulation of digital objects. What are the hidden layers inside your smartphone screen? A sophisticated stack including protective glass, transparent conductive grids, insulating layers, and a display all controlled by specialized chips. This technological marvel combines advances in materials science, electrical engineering, manufacturing precision, and computing power to create the seamless touch experience we now take for granted. With this touch innovation, special gloves and beyond. Ever wondered how some gloves work with touchscreens while others don't? The answer reveals the clever ways we're adapting to this technology. Winter brings a familiar frustration, having to remove your gloves to use your phone, exposing your hands to freezing temperatures just to send the text or check directions. This problem has sparked an entire industry of touchscreen-compatible gloves that solve this electrical disconnection while keeping your hands warm. These specialized gloves face a challenging design problem. Regular winter gloves are specifically made to insulate, to create a barrier between your skin and the outside world. But this insulation blocks the electrical connection that touchscreens require to function. Touchscreen-compatible gloves maintain warmth while creating an electrical pathway between your finger and the screen. I remember standing at a bus stop one winter morning, frantically trying to check my arrival time while my fingers turned numb from the cold. Every few seconds I removed my glove, tapped the screen, then quickly covered my freezing hand again. That frustrating experience made me appreciate the ingenuity behind touchscreen gloves when I finally got a pair. The most common solution involves conductive threads woven into the fingertips. These threads typically contain silver or copper, embedded within the fabric. When you touch your screen while wearing these gloves, the conductive threads act like tiny bridges, allowing your body's natural conductivity to flow through and interact with the screen's electric field. If you look closely at touchscreen gloves, you can often see these special threads. They frequently appear as slightly different color stitching in the fingertips, sometimes forming patterns like X-shapes or spirals. This patterning ensures consistent electrical contact regardless of which part of your fingertip touches the screen. Some manufacturers hide these threads within the fabric to maintain a more uniform appearance. The materials used vary widely. Some use actual metal fibers, extremely thin strands of silver or copper woven among the regular fabric threads. Others use synthetic fibers coated with metallic particles or conductive polymers. All aim to create enough conductivity while maintaining flexibility, comfort, and durability. Beneath the outer fabric layer, these conductive threads concentrate primarily in the fingertips. They run from the outside surface where you touch the screen inward towards your finger, creating a complete electrical path. In higher quality gloves, these conductive elements extend further into the palm area to ensure better conductivity with your skin. The technology continues to evolve with different approaches. Some manufacturers use conductive leather or fabric panels on the fingertips rather than threads. Others incorporate conductive particles throughout the entire glove material. Advanced versions use multiple conductive layers to improve reliability and touchscreen response accuracy. When using these gloves, you're extending your body's natural conductivity through the material. Your finger remains the source of the electrical interaction. The glove merely creates a pathway for this electrical property. Without your conductive body inside them, these gloves wouldn't work on a touchscreen at all. This solution represents a clever application of understanding touchscreen science. By recognizing that screens detect electrical conductivity rather than pressure, engineers modified gloves to become electrically conductive while maintaining their warming properties. Beyond gloves, a similar approach applies to touchscreen styluses. The first generation simply mimicked your finger's electrical properties with conductive rubber or foam tips. These passive styluses transfer your body's conductivity through the stylus to the screen, which is why they typically have metal bodies that you must touch while using them. More advanced active styluses generate their own weak electrical signals. These battery-powered devices create specific electrical frequencies that touchscreens recognize, allowing for greater precision and features like pressure sensitivity and palm rejection. The Apple Pencil, Samsung's Pen, and Microsoft's Surface Pen all use variations of this active technology. Some companies have developed conductive fabrics that can be sewn into any glove, allowing people to convert their favorite existing gloves into touchscreen-compatible ones. Others created removable fingertip covers or conductive sprays and liquids that can be applied to normal gloves. For industrial environments, manufacturers have developed composite gloves with conductive materials strategically placed only at the fingertips, maintaining necessary safety properties while adding touchscreen functionality for workers operating digital equipment in harsh conditions. The success of touchscreen gloves highlights our relationship with digital technology. Rather than adapting our devices to work with existing gloves, we've modified our gloves to work with our devices. This pattern repeats throughout technology history, human adaptation to technological constraints. Looking to the future, touchscreen technology continues evolving. While we've adapted our accessories to work with current touchscreen limitations, emerging technologies may change how we interact with our devices, potentially making special gloves unnecessary or enabling entirely new forms of interaction that don't involve physical contact at all. The future, beyond the touch. What if you could control your screen without even touching it? The next generation of touch technology might eliminate contact altogether. Engineers and researchers are developing systems that can sense your intentions before your finger ever reaches the glass. These technologies represent completely new approaches to how we interact with our digital devices. Several major technology companies are exploring interaction systems that work without physical contact. Samsung has implemented limited hover detection in some devices, allowing screens to sense when your finger is hovering above certain elements. Apple has filed multiple patents for non-contact sensing technologies. Google's Project Solly developed radar-based hand tracking that detects tiny finger movements in the air. These companies are investing billions because moving beyond physical touch creates new possibilities for human-computer interaction. Hover detection represents the immediate evolution of current touchscreen technology. These systems extend the sensing range at the capacitive field above the screen surface. While standard touchscreens detect your finger about a millimeter away, advanced hover detection can sense it from several centimeters. This extended range allows the screen to know your finger is approaching before contact occurs. This pre-contact awareness enables new interface possibilities. Imagine hovering over an icon and seeing it expand with additional information before touching it. Or picture a drawing app showing a preview of your brushstroke as you position your finger above the canvas. These hover interactions create an additional dimension of control beyond touches and swipes. The technology builds on existing capacitive systems, but requires more sensitive measurement capabilities. The electrical field changes from a hovering finger are smaller than those from direct contact. Detecting these subtle changes requires sophisticated sensors and processing algorithms. The screen must also distinguish between intentional hover gestures and hands simply passing over the device. Predictive touch systems attempt to anticipate where you'll touch before contact. These systems analyze hand movement trajectory to predict your intended target. By the time your finger reaches the screen and the device is already prepared for the interaction, reducing response time and potentially selecting targets even if your touch isn't perfectly precise. Jaguar Land Rover has developed a predictive touch system for vehicle dashboards that reduces driver distraction by up to 50%. The system tracks hand movements and predicts which control the driver intends to use. Similar technology could help people with hand tremors interact more effectively with touchscreens by inferring their intended targets despite imprecise movements. Mid-air gesture control systems, like waving a magic wand in the air, detect hand movements without requiring device contact. Using cameras, infrared sensors, or radar, they track hand position and gestures in three-dimensional space. You can swipe through photos, adjust volume, or answer calls with simple movements above or beside your device. Microsoft's HoloLens uses this approach for augmented reality control. Google's projects solely miniaturized radar technology to detect subtle finger movements, allowing users to perform precise controls like turning an invisible dial between thumb and forefinger. These technologies create a spatial interaction zone around your device rather than limiting control to the physical screen. The challenges include distinguishing intentional gestures from casual movements and providing clear feedback. Without the physical sensation of touching a surface, users need visual or audio cues to confirm their actions. Systems must work reliably in different lighting conditions and environments. Equally important innovations are happening in output, how devices provide feedback. Current touchscreens are essentially flat glass that provides no tactile feedback. Advanced haptic technologies aim to create the sensation of texture and physical response on flat surfaces. Systems like Canvas Touch can make areas of the screen feel rough, smooth, bumpy, or sticky without moving parts, using electrostatic fields to modulate friction between finger and screen. Other approaches use ultrasonic vibrations to create localized sensations under your fingertip, simulating buttons clicking or switches toggling. Some experimental systems can even create the sensation of 3D objects rising from a flat screen. These emerging technologies might transform our understanding of what a touchscreen actually is. Future interfaces might exist as interaction zones where hand positions, gestures, eye movements, and even brain activity combine to create seamless control. The glass screen might become just one component in a multi-sensory interface system extending into the space around the device. What if future devices could read our intentions without any movement at all? Technologies like hover detection, predictive touch, mid-air gestures, and advanced haptics are moving us toward interfaces that blend physical and digital worlds more seamlessly, responding to our intentions with less explicit input required. Through the evolution from pressure-sensitive resistive screens to electrically sensitive capacitive technology, and now toward non-contact systems, we can trace a trajectory of increasing abstraction. Each generation moves further from mechanical interaction toward detecting the user's intentions more directly. Will our future devices eventually respond directly to our thoughts rather than physical movements? Extreme touchscreens when the rules change. How do touchscreens work in freezing Arctic temperatures or inside industrial furnaces? The answer reveals the remarkable adaptability of this technology. Your everyday smartphone touchscreen operates within a narrow range of conditions. It expects a room temperature environment and the touch of a bare human finger. But what happens when these ideal conditions can't be met? In extreme environments, standard capacitive touchscreens simply fail, creating a serious problem for industries that need reliable touch interfaces in challenging settings. Imagine an oil worker on an Arctic drilling platform operating digital equipment while wearing thick insulated gloves in temperatures reaching -40 degrees Fahrenheit. Or picture a factory technician controlling a touchscreen interface inside a glass manufacturing facility where ambient temperatures exceed 150 degrees Fahrenheit. Standard consumer touchscreens become completely unusable. Arctic cold makes capacitive screens unresponsive, while extreme heat causes sensor distortions and damages internal components. These challenges have pushed engineers to develop specialized solutions, the tough superheroes of the touchscreen world. Like superheroes with unique powers, each technology variant tackles specific environmental villains. Military equipment showcases some of the best examples of this ruggedized technology. Military-grade tablets and control systems function in deserts, jungles, Arctic conditions, and even underwater. These devices use reinforced glass that withstands impact, pressure changes, and temperature extremes without cracking. Their internal components operate in temperature ranges from -40 degrees Fahrenheit to 160 degrees Fahrenheit, far beyond consumer device capabilities. When capacitive touch technology fails, alternative detection methods take over. Infrared touch systems create an invisible grid of light beams across the screen surface. When touched, your finger breaks these beams at specific points, allowing the system to determine location. Unlike capacitive screens, infrared systems don't rely on electrical properties, so they work with gloves or non-conductive objects in temperatures where capacitive systems would fail. Surface acoustic waves, SAW technology, uses ultrasonic waves traveling across the screen. When touched, your finger absorbs acoustic energy, creating detectable changes in the wave pattern. These systems operate in extreme temperatures and work with gloved hands, though heavy vibration or contamination can affect performance. For the harshest industrial environments, resistive touchscreens make a comeback. While largely abandoned in consumer devices, resistive screens thrive in factories, industrial kitchens, and outdoor settings. Their mechanical operation makes them reliable in extreme conditions, working with any pressure-applying object, ideal for environments requiring heavy protective gear. Consider offshore oil platforms in the North Sea, where workers must monitor critical systems in harsh conditions. Traditional interfaces would fail, but specialized touchscreens with infrared technology allow operators to maintain precise control even while wearing thick insulated gloves. During a recent storm, when temperatures plummeted and sea spray-coated equipment, these ruggedized interfaces continue functioning, preventing potential equipment failures worth millions. Industrial touchscreens operate with barriers between finger and screen. Some detect touches through gloves up to half an inch thick or function when covered with protective overlays. This capability proves crucial where direct skin contact would be impractical or unsafe. Beyond temperature, challenges include vibration, moisture, and contaminants. Construction equipment and military vehicle screens incorporate vibration dampening systems that filter out false inputs from equipment movement. Marine application screens use additional sealing and specialized algorithms distinguishing between water droplets and intentional touches. Waterproof touchscreens represent impressive engineering achievements. Truly waterproof screens operate while completely submerged, using fully sealed housings and specialized detection systems that function when covered with water. Underwater tablets used by marine researchers and offshore workers provide digital interfaces in environments that destroy conventional electronics. Clean rooms and sterile environments present unique challenges. These screens function perfectly while being repeatedly sterilized with harsh chemicals, something that would degrade standard touchscreens. They use specialized glass formulations and sealants resisting chemical attack while maintaining optical clarity and touch sensitivity. Medical-grade touchscreens incorporate antimicrobial materials preventing bacteria growth. Manufacturers must consider human factors in their designs. Workers in challenging environments may have limited dexterity due to protective gear or may experience physical stress from environmental conditions. This drives design choices like larger touch targets, simplified interfaces, and confirmation mechanisms preventing accidental activation. These specialized touchscreens demonstrate how engineers adapt core technologies to meet specific challenges. Rather than forcing users to accommodate technological limitations, these systems are engineered to function where needed most. This adaptability has allowed touchscreen interfaces to spread into virtually every industry, creating a universal interaction method across an incredible range of conditions. Now that we've seen the full spectrum of touch technology, let's wrap up what we've learned about the science behind this everyday wonder that connects us to our digital world. The next time you tap on your phone screen, remember what's really happening. Your finger disrupts an invisible electrical field that extends just above the surface. Your body, a natural electrical conductor, absorbs some of this field, creating a disturbance that tiny sensors detect and locate with incredible precision. This interaction represents a complex fusion of physics, materials science, and electrical engineering working together to create the seamless experience we take for granted. Touchscreens have transformed how we connect with technology and each other.